Antimatter. Sounds like science fiction, a material that looks like ordinary matter, but would unleash as much energy as an atomic bomb if even a speck of it came into contact with anything around us. Chances are that you first encountered the concept of antimatter in Star Trek, where it's used to propel spaceships. Or maybe you've read Dan Brown's novel Angels and Demons, in which antimatter makes the ultimate bomb. If so, it may come as a surprise that antimatter really does exist. In today's episode, we will be looking into the mysterious and elusive substance known as antimatter. Every type of elementary particle in nature has its own antiparticle. Particles and corresponding antiparticles are very much alike, except they have opposite electrical charges. For instance, the antiparticle of the electron, known as the positron, has the same tiny mass. But while electrons carry a negative electrical charge, positrons are positively charged. English physicist Paul Dirac predicted the existence of antimatter back in 1928, based on his quantum theory for the motions of electrons. Just 4 years later, his American colleague Carl Anderson discovered positrons in his cosmic ray experiments. Physicists are faced with a nagging problem. The energy of the Big Bang should have been converted into equal amounts of matter and antimatter. Yet here we are, in a matter-dominated universe of galaxies, stars, planets, and people, with only fleeting amounts of antimatter. At the beginning of the universe, there was a tiny imbalance making more normal matter than antimatter. In 2011, a small difference in behavior was found, but it's not enough to explain why there's so much matter in the universe. Even after many years of research, this remains one of the biggest mysteries in science. Could half of the galaxies in the universe be made of anti-atoms, anti-molecules, and anti-stars? Is it possible that there are isolated areas of antimatter in the cosmos? Probably not. There is enough matter between galaxies and clusters that would cause annihilation, but we don't see the gamma rays that would be created if this were the case. In 1928, Paul Dirac made his astounding claim, making antimatter the focus of unprecedented attention. It was a spectacular achievement and one that won Dirac a Nobel Prize, but its implications were perplexing. Like quadratic equations familiar from school math, Dirac's equation had not one but two solutions. One of them made perfect sense and described the properties of that most familiar of particles, the electron. But the other solution seemed to describe another subatomic particle, whose properties were the exact mirror image of the electron, with the same mass but opposite electrical charge, an anti-electron. What worried Dirac was that no one had ever seen such a particle, or anything like it. Even so, he decided to put his trust in his equation and regard the new particle as a prediction. Dirac's faith was quickly rewarded. In 1932, physicist Carl Anderson at the California Institute of Technology had developed a new type of particle detector to study cosmic rays, incredibly fast particles hurtling through the atmosphere from deep space. A photograph taken with the detector revealed something utterly bizarre. The trace of a particle behaving as if it were the exact mirror image of an electron. It was the first time anyone saw the particle that Dirac's equation predicted 4 years earlier. It had the same mass as the electron, but a positive charge. They named it the positron. But this discovery made the mystery of antimatter even clearer. There was nothing in Dirac's equation or in the laws of physics that explained why the universe favored matter over antimatter. So where was all the antimatter? One suggestion was that the Earth just happened to lie in a relatively antimatter-free region of the universe. Perhaps there were whole stars made out of the stuff lurking out there. If so, it would be easy enough to tell, for as soon as antimatter comes into contact with ordinary matter, it is totally destroyed in a huge burst of radiation. Einstein's famous equation E equals mc squared shows that if just a single gram of antimatter comes into contact with ordinary matter, the energy released is equivalent to the detonation of an atomic bomb. Matter-antimatter annihilation is the strongest energy source in the universe, and its effects are very noticeable. If there are anti-stars or even anti-galaxies out there, the Earth should always be surrounded by gamma radiation, which is a clear sign of matter-antimatter annihilation. The reality is like a cosmic roller coaster. Since the 1960s, our space explorers, known as astrophysicists, have been launching supercharged gamma-ray detectors high above the cozy blanket of our atmosphere, ready to uncover the secrets of the universe. And guess what? The message has been crystal clear. There are no strange antimatter objects hanging out anywhere in the vastness of space. As a possible alternative solution, Neil Turok of the Perimeter Institute for Theoretical Physics in Canada has suggested that the Big Bang not only produced our known universe, but also a mirror universe, consisting of antimatter and evolving backwards in time. That would restore the symmetry. However, it's a very speculative idea, to say the least, and all but impossible to either prove or disprove. Future studies on antiparticles are important. Better data from space detectors might help us understand antimatter one day. In true Star Trek jargon, physicists need to boldly go where no man has gone before. This concludes today's episode of the Paranormal Report. If you enjoyed today's episode, please give us a thumbs up and consider subscribing to our channel. It is due to your continued viewership and support that we are able to bring you interesting and informative videos like this. The team here at the Paranormal Report really appreciates your support.